And we're ready.
All right. I think I'm ready. I think I've got like the 15 things good to go. All right. Welcome back, everybody.
And we're ready.
So, okay, so I had originally planned to go right into control through contact, but I've had some good discussions with people in their projects and the like, and I couldn't help but stick this lecture in. I feel like there's a few things that the field knows that I want to make sure you know about how powerful parameter estimation can be in the context of manipulation like this, and certainly for the robot, maybe even for the things you're picking up, and how that plays into adaptive control. So I'll talk more about estimation than adaptive control. You could take an entire semester on adaptive control. I'm just going to give a teaser. But I thought I'd do it in the context. A few of you for your projects are doing things related to tossing, right? And I think this tossing bot project captured a lot of imaginations. This is, I'm not sure if the audio is playing for you or not, but roughly Andy and company made this robot throw objects into bins. Actually, I think I will let the audio play here, see how badly that goes.
The audio got me.
Okay, so I will leave my audio off and let people's audio play, I guess. But I want to let this play for a minute. There's a couple really good points being made here. So first of all, the pre-throw conditions. He says if you pick up the screwdriver at a different point, it'll take a very different trajectory. Now we throw a ping pong ball, aerodynamics maybe come into play, so you get a different trajectory out. I want to read the paper about darts. I haven't seen that one. But... Okay, I just want to get to a key part here. Okay, so I think one of the big ideas in the paper, I guess, was this idea of combining physics with deep learning in order to throw. So you have the basic physics-based understanding of maybe where the ball would go if it was just projectile motion, but then you can learn to throw bananas and ping pong balls and screwdrivers with a residual model. And one of the best things about it, if I go to the next slide here, I think my favorite part of the work is actually the way it's throwing, the way it trains is it throws into a bunch of different bins. And then super good to just automatically reset and then keep throwing. That's like, that's the best part. Okay, so I think that's a cool recent paper that I think the idea of learning these residual networks is extremely good. I just want to make sure we understand what we could have done, before that piece of that work. So let's look a little bit at the assumptions here, and we'll think through a few of the details. The controller assumes that the model-based controller, the physics-based controller, assumes that object is a point particle, and that the aerial trajectory of the projectile moves along a ballistic path. And we'll write some of the equations down in a minute. So that's the basic, physics model. And they point out, I think correctly in the paper, I mean, there's even in their description, they say there's two major phenomenon that cause this to not be a good model. I think one of them is the fact that you're often not grabbing the object at the center of mass. So if you pick up an object and its center of mass is far from your grasp, and you control the velocity of your hand when you let go, it's really the velocity of the center of mass that matters. And we'll see that in the equations, not the velocity of the hand, and that can lead to a very different trajectory. Okay. And I have to believe that's kind of the dominant effect, the dominant thing you'd have to learn. The aerodynamics, I think, was the second thing they called out. I think the aerodynamic, maybe for the ping pong ball, the aerodynamics are significant, but I don't think aerodynamics are a major factor in the projectiles that they're throwing. So I want to question, how well can we estimate the center of mass of the object before we throw it without any learning? Instead of like learning from pixels and everything, picking up the grass, what if we just pick up an object, move it around a little bit, use our torque sensors to estimate the center of mass of that object, and then do a more accurate throw? How well would that work? And that's what I want to sort of talk through today. This is a 1991-ish video from Jean-Jacques Slotin. It was actually, the paper was never published, but this was an adaptive controller, which would pick up a mass. I'm going to mute my thing again there. Pick up a ball of unknown mass, go like this to estimate its parameters, and then, throw it into a hoop across the room really well, I think. So so now you're looking down the, down the chute of the hoop. That was just to get it to a known position in the hand, and then sunk, slam dunk every time. So there are some very, very powerful ideas there of just, parameter estimation and adaptive control. And I think the newer work on learning and learning residuals can improve on that in important ways. But I want you to understand that there's some things where we have almost closed form solutions for that go a pretty long way. This was actually a series. There was a series of papers that were sort of around that time from Jean-Jacques' lab. By the way, that arm is the WAM, the Barrett WAM arm. This was actually like, I think Barrett WAM #2 or something like this, and because Bill Townsend is in town and was in the lab for a while, and they were building this. This was also the time when Ken Salisbury was here building incredible hands, including the MIT Utah hand, which I'm gonna have to show you when we get to the dexterous hand stuff. But so they did a bunch of really clever things. They didn't have like computer vision the way we do now back then. So what they did is they had foveating cameras, right? So there's two cameras at the top here if you watch them carefully, and the scene is such that there's like a bright white ball or something, or a bright orange ball or something like this. And all the vision system knew how to do was keep the bright white or orange ball in the center of the camera, and then it's very easy to track the center of the bright white ball, and then use the encoders on the camera to track the ball. So that's what you did like before we had deep vision. But this was a series of projects where they would also do catching, right? And they'd throw it back. And we'll talk about the type of models that they learned and estimated with least squares, but they were pretty rich. Certainly they could learn the parameters of the ball and the robot, but if you fast forward, you'll see that they're also learning to catch paper airplanes, which have significant aerodynamics, I would say. And there's a second video here of actually explicitly focused on catching the paper airplane, tracking and catching the paper airplane. And they used, you could think of it as a linear network, or a linear function approximator based on nonlinear features to learn the aerodynamic terms that they didn't have from their first principle models, and they'd grab an airplane out of the air. Okay, so I want to sort of talk through some of that. And if we were to fast forward somewhere along here, there's a nice, yeah, right there. Stable real-time prediction of the trajectories of light objects in air using wavelet networks, right? So it's just like, how does all this stuff work together? Like, what does that do? And how does that compete with a deep network? I don't know, but this went farther, I think, than people remember today. Okay, so let's think about parameter estimation and throwing random objects, bananas. Okay, so the first thing I think to think about is the ballistic trajectory of an object, of an inertial object here, of a rigid object. So one of the things that I guess you know, but you have to remember is that, and actually Andrea and I were talking about it the other day. She's doing catching for a project, and I said, "Are you estimating the mass?" And then I realized you can't estimate the mass of a flying ball. That you just have to. If you're watching a ball through the air, there's no way to tell if it's a 10-pound ball or a 5-pound ball, right? Because the equations of motion are just in the air. They are mx double dot equals 0, right? Which implies that x double dot equals 0. Mass does not affect the trajectory of the ball at all. And mz double dot equals negative mg, right? So z double dot equals negative g.
You're bored.
Mass has no effect on the, I see that I missed my window a little bit again. I'll remember to write low. Mass has no effect on the center of mass of the ball, right? But so let's be careful here. The x and z here, I just said I was going to miss the top, and then I wrote on the top.
Sorry, I think we're still seeing the slides.com.
Really? Oh yeah. Huh. That's weird. Give me a second to figure that out. I'm going to restart my sharing. Hopefully that works better now. Let me just test if I can flip back and forth. That's working, right? Yeah. Okay. Don't know why that didn't work for a minute, but let's hope it's better now. Okay, so the ballistic trajectory, which I will, now you don't even know why I was talking about it being too high. Okay, the ballistic trajectories are mx double dot equals 0. These are the equations of motion of where x and z are the location of the center of mass. Right? Not some arbitrary, before most of us was born, Terry, thanks. Not some arbitrary point on the body that you've chosen as your 0, 0, 0 in your SDF file, but it has to be the center of mass. It's the center of mass that goes through that completely ballistic trajectory. Similarly, you can ask about the rotations. Maybe you want to flip a bottle and have it land on its upright, or you want to, I don't know, the banana has to get in a certain orientation when it lands. So again, we have conservation of angular momentum about the center of mass, right? So I theta double dot equals 0 in the planar case because there's no moments acting directly on the robot, and I is the moment of inertia about the center of mass. Okay, so that also implies that data double dot equals 0, and I just don't need to know the mass and the inertia if I know when the ball takes off, if I know its center of mass location, or the banana or whatever takes off, I know its center of mass location and velocity and rotational position and velocity, then I know everything about how it's going to evolve without estimating the mass. Okay, so so do you even need to estimate the parameters of the ball in order to do the tossing? The reason you need it is because your goal is to control the takeoff velocity. So you need to know at least where the center of mass is relative to the hand, so that as you go to take off, the thing that you're regulating should not actually be the center of the gripper, right? It should be the center of mass of the object, okay? So at very least, when you shake it around, in fact, the only thing you really need is the center of mass of the object in the hand coordinates, okay? Now, it makes sense to actually, it turns out to not be harder to estimate the inertia matrices at the same time, and you kind of can't, you can't pretend you know them, you'd get the wrong answer. So we're gonna estimate the mass, the center of mass, and the inertia, which is the entire spatial inertia of the object all at once. But we really only need the center of mass, right? Right, so the trajectory depends on initial velocity of the center of mass. Okay, so you might, I guess there is a case where you might need the mass and inertia of the object more completely, and that would be if it affected the dynamics of your robot in any substantial way. If your goal is to build, you know, a robot that is at sort of at the limits of its performance, or even close, where like a PD controller is not good enough, you really have to take into account the fact that the weight, if you're going to throw milk jugs, for instance, with a WAM, then suddenly the, you know, estimating the mass of the milk jug is going to affect the ability of the robot to open its hand at the right velocity, right? So you might need the additional information for tracking, but assuming that the object is light relative and you can track with high gain feedback and get to a good takeoff velocity, then it's really only the center of mass that you need. All right, so the thought experiment I want to have here today is let's just say we've picked up an object. I'll even, for the math, we'll just assume that it's welded to the hand for now. So we won't assume that there's any dynamics of the sliding, although if you can measure any movement in the hand, that would be enough, okay? But let's just assume it's fixed. That just makes my equations easier. And we're gonna shake the object around, try to estimate its parameters, and then, you know, then we can do our throw. So let's dig in a little bit to the structure of multi-body parameter estimation. So if I just think of this as an arbitrary bag of equations that I can learn with a deep network, I don't doubt that we can learn it with a deep network, but we would be missing out. In fact, in the naive form, you would be learning a much harder equation than you need to learn. And let me try to make that point. So I'll start just with a super simple example. I mean, so the key idea, actually, the key idea is that the inverse dynamics, not the forward dynamics, but the inverse dynamics are actually linear in the parameters. In the lumped parameters. And I'll tell you what that means in a second. Okay. In fact, if you take the forward dynamics, if you take your simulator and you try to learn the forward dynamics directly, then it's no longer linear in the parameters, and it's a much worse problem to do. So you're actually much better off staying in inverse dynamics form than to use the forward dynamics model. And you can see that even just on a simple pendulum. So if you remember my mass, length, gravity, theta, the equations of motion, I've got some damping here. Okay, so let's say we don't know mass, length. I mean, okay, if you don't know the length, you should just buy a ruler probably. But let's say we have to estimate the parameters. Gravity, maybe we can assume we know, but let's just say we have to acquire all of them from data. So the observation is that the structure of this equation sort of separates neatly between the data, which in a system identification or parameter estimation is our thetas, theta dots, sine thetas, our theta and our taus, with our parameters. So let me rewrite this as, wow. Theta double dot, sine theta, all my terms that are sort of dependent on the data, times some parameter vector p equals tau. Okay. Just simply rewriting the equations, right? Clearly, this is a linear set of equations in P, rather. And this, when I have data from theta and tau and theta dot, for instance, then this is just this is just numerical. So sine theta is just a constant also. It's just my data. So this is just going to be a big data matrix if I list out a bunch of them. Okay. This is just data. And the only thing I'm trying to solve for is a vector P. And this vector P, these are the lumped parameters. And for most of the work we'll do today, we're not going to estimate mass specifically by itself. I'll talk about a little bit about when you can, or the length individually. What we're going to estimate are these lumped parameters. And or even more accurately, we'll estimating a subset of those lumped parameters, or a low dimensional version of those lumped parameters, which are the identifiable lumped parameters. And that's something there's a lot of understanding about. And it's not somehow, I mean, there are a few cases where you might actually need to know mass and length by themselves. Like if you wanted to, write your results of your system identification to an SDF file and then send it to your friend or to your other process and, to your controller or something like that. There might be reasons like that, but actually it's only the lump parameters that affect the dynamics. So they are the only things that you can estimate from the data, and they're the only things you need in order to predict the future. So if you have ML, if you have ML squared and MGL as independent terms, then you have everything you need to predict the future in these equations. It's only somehow the natural parameterization that we write in URDF and the like is in some sense an over parameterization of the problem. Okay, so if, yeah.
In this particular example, if we assume we know G, then we could get everything. But that's just unique to this example, I would think. But is that?
If you assume you know G, then you could back out M and L, yes, and then you could get everything. That's true. This particular example.
Yeah, that's just this example.
And you have to, yes. So for instance, if you can check, I'm just checking my physical quantities, but if torque was 0, we shouldn't be able to estimate the mass of the pendulum, and that is true. But you're right. If in this case we know G, we could actually back them out. And there are cases where you can back it out exactly, but they're rare. And I think the more important case is when you can't, the more general case. I'm sorry, I just saw the chats. Since gravity acts on the center of mass, even in the 3D case. Oh, I just said this in the planar case, so I didn't have to write a 3D rotation. That was just, yes, but you're absolutely right. Same thing in 3D. Good, yep. Okay, so let's collect data. Which fundamentally is in the form of trajectories of theta and torque. And then we'll form the data matrix, or we'll form the observation matrix. Can I call this term here W? And we'll form the observation matrix big W, which is just going to be all of our data stacked up. Like this, okay. And then same thing for tau on the right-hand side. And we now just can solve for the lumped parameters using least squares. Okay, so this just becomes a big WP equals, in general call the right-hand side Y, but let's call it tau for now. Now, let's think a little bit about what that least squares problem is going to look like, right? So, like we said, there can be cases where not everything is observable. So, for instance, or is identifiable, I should say. For instance, the mass of the ball should clearly not be observable if I just observed it flying through space, right? So how would that play out? So if I had mx double dot equals 0, right? Then if I write the data matrix, whatever, I'm going to get a bunch of x double dots, which are going to be 0, right? I'm going to get a big 0 matrix times m equals 0. It's going to be deficient, right? And there are other cases where you would expect to have written down your equations that have parameters, but there is nothing about the trajectory you're observing that can account for it. Like we said, if the torques were always 0 and you dropped your pendulum, then you would not be able to actually estimate those parameters. So what does that mean sort of in terms of, well, in terms of practice, somehow identification is going to require some sufficiently exciting trajectories, as in parametrically exciting, I guess also, for personal interest exciting, but so some sort of sufficiently rich trajectories. They can sometimes called parametric excitation. And actually, some of the equations we'll write will give a prescription for how you might do that. In fact, this can be actually a nice motion planning problem. For instance, people will do trajectory optimization in order to find a trajectory which will move the robot through in order to maximize an information metric on the rank of that data matrix. Basically, somehow a condition number of that of this data matrix, you can actually design a torque so that that matrix has a lot of information in it. Okay, but we would like ideally full ring. We can't always achieve it. A lot of times there are parameters that you just simply can't know. In that case, we talk about the identifiable lumped parameters. Which in practice, we don't get the state-of-the-art algorithms for finding which of your parameters are identifiable typically runs through getting a data matrix and just doing numerical linear algebra on that data matrix, do basically SVD on that data matrix, singular value decomposition. And that can tell you the subset of your, or the subspace of your lumped parameters that are purely identifiable. So take an example, for instance, the equations of motion for our EWA, right? So in the URDF, we clearly have moment of inertia for all of the links. We have the kinematics of the arm and the like. But if you think about the first link, right? Nothing we are ever doing with the robot is we're only ever rotating that first link around one axis, right? Because there's only one axis between it and the world. So there are directions in the inertia matrix that we simply cannot measure, cannot excite, right? So any reasonable sort of natural parameterization of the EWA identification problem is going to need to admit that it can't estimate those parameters. And it's not bad. You don't need to estimate those parameters in order to predict the motion of the EWA, right? Somehow you just never needed to write them in the URDF. They were sort of irrelevant until you need to carry the EWA to a different lab. Okay, so that's the very basic setup, is this idea that we're going to write the lumped parameters. Let's think about how it looks in the multibody case, in the more than the pendulum case. Okay, so the equations I've written a few times throughout the term here of our mass matrix plus our Coriolis terms. Oops. I will not include contact forces right now, although I think actually you can include them if you can measure them, but let's not include them yet. It turns out even in the more complicated cases, we can actually still write the equations as linear in the lump parameters. So this is now a big complicated equation, matrix, right? With ML squareds and stuff like this inside it. But it turns out all of the terms are still linear in the lumped parameters. Okay, so let's look at, for instance, the equations of the simple double pendulum, which is just the two-link arm. I'm sorry to scroll up here, but it's this arm here, right? So it's the two-link version of what I just wrote. The equations of motion, if you write them out like this, you know, you've got a bunch of L squared kind of terms. You've got some cosines appearing. You've got some sines appearing. Remember, I use C and C2 for cosine theta 2, S2 for sine S of theta 2, right? There's, you know, it starts getting complicated, but still there's a separation that occurs in all of these Lagrangian mechanics problems where the variables of your state are multiplied by your parameters, but in this sort of simple way. So, I mean, really, what it means is that you're never going to have, you get sine of theta, you know, cosine of theta kind of terms, sine of theta 1 plus theta 2 down here, but you'll never get sine of L theta or sine of M theta, right? These things are always separable. I actually made that point when we were talking about kinematics being polynomial before, right? Somehow it works out that the terms are always simple in simply divisible between theta and masses and lengths and stuff like this. So in practice, we can actually still do this lumped parameter trick in a much more complicated set of equations, potentially, right? You now have a set, you know, this is now a series of equations, right? In the two-link, there's two equations for each, but you can still separate them out. All of the, you know, cosines and the like times a single parameter vector equals my other, and I'll just have two equations now instead of one. Okay, and then I will copy all of those equations down for my data matrix. I think that's sort of crazy and super nice. Okay, so if I did my forward dynamics, which is what I have in a simulator or something like this, right? Then I've somehow taken an M inverse, right? I have V dot equals M inverse times all this other stuff, U minus or plus tau G minus C. Okay, this M inverse is, you know, makes either I have to somehow come up with rational lumped parameters, but even then, I've got sine thetas mixing in weird ways. That breaks the linear in the parameters property, okay? And so if you don't sort of stay in torque space and you switch to acceleration space, then you've lost all this beautiful structure. So if you're doing, you know, residual learning or model learning or whatever, you know, I think it's a good question to ask is, you know, should you be doing it in Q in theta in Q double dot, or should you be doing it in torque space? Because it's, even if you don't start with a parametric model, it seems like the equations should be better in this space. So let's stop for a minute and think about how you implement this, right? So it's actually relatively hard to type something like this in. In the past, I think it would typically involve a small labor of love, which with you know, writing out the equations yourself, even for an EVA or something like this, and typing them in. And even today, there are very few simulators that can give you access to the equations of motion in this form so that you can manipulate them in this way. but we do have a symbolic backend in Drake. So let me show you that. And here's a Jupyter notebook. Okay, so I hoped to push it to you before lecture, but it's not quite done, almost done. All right, so, but let me show you that we have symbolic dynamics in Drake. So for instance, if I just want to take my 2-link EWA, which is the same EWA, but I just welded most of the joints, we can do symbolic dynamics for bigger EWAs, but you don't want to see me print it out, right? So the equations get pretty big pretty fast. We have this fancy thing which is changed to symbolic, and you get a symbolic version of your plant. And then, so by default, the symbolic version of your plant just has a bunch of symbolic variables that are holding double values, and it will act like the original one. But if you go in and say, you know what, I want a few of these elements to be variables so that I can track them, and you write those into the context, then you can calculate the inverse dynamics and print it out and get, you know, for whatever robot we're working on here, you can get the symbolic form of the equations of motion. If I were to, you can see it's already pretty big. Admittedly, there's some simplification that I didn't run, but you know, there's some small numbers and everything, but equations of motion get really big really fast. If I had taken the M inverse, it actually, I think it might have complained. No, the 2x2 case it'll do, but we don't even support the full M inverse because symbolic matrix inverses are crazy. Okay, so so this is cool, right? So I can actually see, you know, the equations of motion. And what's also interesting, so this is one that we could have zeroed, and there we do actually have tools. I should have just written that to zero out the small coefficients, but I can basically, you know, write out the full equations of motion. But in this example, the masses, link lengths, and everything were just numerical values still, and so I get a numerical coefficient times this. Now that's super important, is this interleaving. If you compare this to like Wolfram's symbolic engine, Wolfram will do everything in rational arithmetic. It's like, I think, the best out there. You know, in my experience, it's incredibly good and it's super powerful if you want to prove things and the like. But and then they have made it scale beyond what I would think you'd want to scale. But this is the symbolic we've chosen to implement, and a lot of other packages that do symbolic will implement, is a combination of floating point and symbolic, right? So it's not trying to prove something absolutely by keeping explicit rational numbers. We've accepted there's some floating point errors. We have e to the -47 garbage, but this will scale a lot better. We can take advantage of floating point arithmetic for the things that we don't care about the symbols for, and use symbols for the rest. Okay, so how would I set up the data matrix for, so if I've now taken a 2-link example, although this one I could have done n links, the full EWA, and I'm gonna just take the mustard bottle and weld it to the hand. Why not? And then the interesting thing will be, can I wave it around, and without knowing the parameters of the mustard bottle, can I back out the inertia and mass and moment of inertia, the center mass, moments of inertia of the mustard bottle. Okay, so slightly different workflow. I'm going to change it to symbolic, create my context, and then I'm going to make the spatial inertia. I'm going to set the inertia of the one body that I care about to be the variables. So I can even, let me do this slightly differently so you can see. I'll do mass and just center of mass. So this is, I know it's ugly reading code, but you know, I've got a spatial inertial object which takes the mass, center of mass, and I've made variables for the moment of inertia. These are the kind of variables you'd see in your URDF file, okay? And I've just set the spatial inertia in the context to be the symbolic one. So I'm going to track just that. And then I'm going to, again, make some, I'm just evaluating it at one point with some random accelerations, some random forces. And then let's see I just broke it, didn't I? I'll do the one that it worked first, and then I'll change it. Okay. So, so there's two equations, right? The first one is corresponding to tau 0. Okay, that's the equations of motion of the first link. And tau 1 is the equations of motion of the second link, because the inverse dynamics are in tau in torque space, right? Now I get a more manageable set of equations where I took advantage of the floating point arithmetic to do all of the floating stuff, okay? And I just have the mass, center of mass, I, and the like up here. Now, the reason I set the mass that I had gone back through and set the mass equal to 1 and lumped in the mass center of mass is because I just cheated and did the lump parameters myself. We have code actually that will extract the lump parameters for you and do the insertion, but it's just a few lines that we didn't need. It was trivial in this case. The only time the mass entered the equation was over parameterizing. It was multiplying times the center of mass and center of mass 0, 1, and 2. Okay. So I calculate the inverse dynamics and I printed out tau 0 and tau 1. And then I can extract, so from those equations, I can extract basically the A and B, the data matrix and the Y matrix, okay? So I've got my Y and then my W and Y data matrices, and they come out like this, right? So I expect W for this system to be a 2 by number of parameters, and my Y to be 2, because I've got 2 equations, yeah? So if I now want to estimate mass, center of mass, and the like, all I have to do is run the robot a little bit, move it around, have it be sufficiently exciting. If I just set torque to 0 and let it fall, that might not be enough to recover the parameters. I would see that the data matrix has insufficient rank. But if I wiggle it around enough, especially with the 3D robot, and just do least squares on that, then I can recover the parameters. And I will provide that tonight. I got it almost working. Had to add some bindings late last night. Okay, so any questions on that?
I have a question, Russ. So if you have enough samples such that the problem is like over constrained, like in this specific simulation setting, is the error of the least squares problem going to be 0? Like your model is exactly what you defined the dynamics as?
So, okay, if my accelerations were perfect, right? So then you could obtain 0 error, but that's absolutely a weird corner case. I think even in simulation, if you simulate trajectories with some ODE solver and then tried to back out the accelerations, for instance, you would see some residual there. Having too many rows in the matrix is what you want, right? You want to be in the case where you use the power of the data to be fighting down any of the noise in your measurements, right? And certainly there's cases where, yeah, I mean, we're actually gonna, that's what I'll say next is the formulation I've showed so far of using Q double dot, that's something that's sort of reasonable to do in simulation, but actually, there are better choices for choosing those, you don't want to assume you have noise-free acceleration measurements on real robots. So yeah, I think in the one corner case where you've calculated everything perfectly, you could put it into the matrix and come back, you'd get close to 0 error. Okay. All right, so the parameters I wrote there, and in general, the parameters of the single rigid body spatial inertia. Which is just the 6x6 version of the concept of inertia, you know. It lumps the center mass and everything together. So the parameters are, you know, the mass, the location of the center of mass, and the inertia, the unit inertia that which we tend to parameterize as a bunch of parameters, ix, x, I, y, y. This is how I wrote it down just a minute ago. So 6 inertial parameters. Now, there's a couple things about that. So I already said we can't separately identify these from the mass. So it makes sense to lump in the mass and the center of mass if this is somehow an over-parameterization. So I set this to be 1 and allowed the center of, and instead wrote m times p center of mass. And this would be sort of m times the unit inertia, okay? But even then, there are more advanced things I could do. I think the approach for doing the mustard bottle and figuring out, or even throwing a banana, I think probably just doing least squares on this is gonna be just fine. But more generally, there are things to be careful about, right? So this is 6 numbers to represent a 3x3 matrix, because we're assuming it's symmetric, okay? But not all values of this will define a physically plausible inertial matrix. Right, if your 3x3 matrix has to come out of something that has mass and density, you know, then it can't actually, there are extra constraints besides it being a symmetric matrix. There's a nice paper from Patrick Wensing, who was here in Sangbei's group a few years ago. I'll cite it in the notes. On how you could add that to add the constraints to make physical plausibility for the inertial matrix, you know, add that in and try to solve for only physically plausible inertial matrices. That's a detail that most people don't include. It's a nice thing to include, okay? It's cool that it's easy to add. So like, I don't know. So I think it's super cool that we have like LMI solvers and symbolic equations of motion and, you know, and all this like sitting in one toolbox, because there's things like that you can kind of, oh, I can put that together and it's pretty easy, which is pretty rare. Okay, so but the biggest problem with what I've written above is assuming we can measure clean estimates of the acceleration. And there's a bunch of different approaches that people consider to be better, you know, just flat out superior to assuming Q double dot. You know, as I was writing this up this morning, I was thinking that you know, there might be some time, and maybe it's even here. Maybe at some point, maybe that's just gonna be an too old thing. Maybe we can just you know, we have high enough quality sensors and they're running at high enough rates that we can somehow get accelerations perfectly, and everything I'm saying is like old school. I don't think we're there yet. I think right now it still sucks to use accelerations. So there are a couple of different alternative formulations. It turns out that there's a way to basically, I mean, you fundamentally can't ask for the torques to match the accelerations anymore. So what do? Well, You can filter both the left and right half side of the equation and look at basically the longer term effects of the acceleration changes at the torques. And that is a way to actually, you have to sort of convince yourself in the algebra that it is removed a Q double dot in any effective way. But so slow teens, add a low pass filter. And that can get rid of the accelerations. But I think the more common solution to this, which Slotine also mentions, but is to switch to writing things in terms of energy and power and change of energy instead of doing it in terms of torques and accelerations. So if your constraint equations and this is called the power formulation. If you, instead of writing torque equals something, you can say that my torque times velocity, which is the total power, has to equal the time derivative of the change in energy that you expect. And in all the physical quantities we have in our equations were derived through this Lagrangian, then we can write our expected change of energy as a function of those mass parameters. And this fundamentally gets rid of Q double dot. It's a different mathematical object, right? So somehow we did have n equations for every data point. And now if we're just checking the total power, we only have one equation for every time sample. So it's a different thing to work with, but it seems that people consider it superior, mostly due to the fact that you don't need the Q double dot. Mostly favor these sort of power formulations.
In practice, does it change how much time you have to spend waving your object around before you can do anything with it?
Yeah, I've never seen that articulated as a limitation of it. I mean, does it take n times as much data? I'm not sure, because it excites the parameters in a different way too, right? So I think the time that you're spent is probably not dominated by the number of sample points, but how long it took you to get to different parts of the trajectory that turned these things on. And I don't, that excited all of the parameters. And I don't know that that's fundamentally different in this case, but it is a good question. Okay. There's a bunch more things to know. In fact, like if anything, I would say, I want to give you the sense that people know a lot about this. They know, exactly about what sort of identifiable lump parameters happen on different robots. They know how to find them reliably. They know the numerics of these different formulations, right? So I don't want us to throw all that away. And learn, I think we should use deep learning to learn residual networks, but probably the coordinate systems you choose matters, and the exciting trajectories is going to matter. That's not some problem of our algebra. That's going to be like a function of what's identifiable, and the deep network's not going to do more than these methods on that. So I think there's a lot to know here. There's also something sort of fundamental here that I want to call out to. So the one thing that I think is a major limitation of the parameter estimation I'm talking about here is that this is taking a view that you're only comparing the difference between your model and the data effectively one time sample at a time, or at every time sample independently. And so that is somehow people call that an equation, or there's various different names for it, but you'll see it in all the system ID literature. There's always grouped into these two different approaches. One of them is, how well does my model predict the data if on every time step I reset my model to the data and then do one step? I reset my model to the data, I do one step. And that's what I've written down here. And that is the one that you can use least squares for. And that happens often in many of these system ID formulations, is that you can have somehow a nice or a convex parameterization of the one-step error. The alternative is to say, I'm going to set up my model at the initial conditions at time 0 and my data at time 0. I'm going to integrate my model forward open loop and compare the integral error that is accrued, right? And that's called simulation error. And it's generally considered to be a much more robust object, right? So, but it's harder. It becomes a non-convex optimization. So a lot of times what people will do, they'll use the equation error and all this structure and math to find the initial guesses of the parameters, and then they'll fine tune with a nonlinear optimization to do the simulation error. And the reason that those things are different is it is possible to describe your one-step data fairly accurately, but get even an unstable, like even in linear systems, people know this. You can find a linear system that describes the data, but is unstable, and therefore will have a long-term error that is very big. So people, there's lots of ways around this. Some people try to do the one-step error times with some constraints for stability of the system and all these other things. But I just want to call out that everything I've said so far today is this sort of one-step view of system identification, and there is a potentially more robust thing to do where you just simulate it forward in time. So if your robot only has position plus torque force sensing, can you simply pick a bunch of static positions and estimate the parameters in a similar way? Tell me what you mean, Sebastian. I don't quite get it.
Yeah, so instead of prescribing or measuring the speeds and accelerations, if you just move your robot to a bunch of static positions and just compare what the gravity torque to hold up the arm itself plus whatever it is when you're holding the object in grasp, and just getting a bunch of those different positions and formulating similar least squares problem.
Cool. Yeah. So I think the way you said it is perfect, and that you can tell there's going to be some limitations to that. So you can get all your statics from that, but you can't get your dynamic terms, right? So all the velocity dependent terms would be hard to get that way. Joint damping and stuff like this would be hard to get that way, but certainly you can estimate inertia matrices that way.
But if you're just estimating like mass and inertia of your in-grasp object, that's fine then, right?
Yeah. I think you're right, yes. Yeah, perfect.
Thank you.
Okay, so people also write in residual models in this sort of least squares parameter estimation framework. And it won't surprise you really, but you'll put a term like this in, and then you'll put in some huge, potentially huge set of parameters times some nonlinear basis functions, right? You could have it on potentially all of the terms, okay? So some nonlinear basis functions with linear parameters. And the power of doing that, I mean, the alternative would be to put a deep network here. You can do that, but then you're in the space of doing gradient descent. And in this case, you can still do least squares. And these nonlinear basis functions can be surprisingly rich. So there's a lot of work from Jean-Jacques Lotine and others of using, for instance, radial basis functions for this, using the wavelets like I showed for the airplane catching, and I don't know. I think it's extremely interesting to ask how much we've gotten, what is the gap. If we were to put all of our best tools like this at the tossing problem, for instance, I do think that the representational power of the deep networks is going to be stronger. I think this case, so I think in the Andy Zhang version, from experience, I can learn some parameters of my throwing, so I don't have to do any online identification. In this case, I could pick up any object I haven't seen before, no learning required, and do a little estimation and then throw. So that there's slightly different things, but I would love to put them head to head and really understand what the best version of this could do compared to the best version of the learning solution that Andy did. Okay. Let me just give a bit of a teaser for how this plays into some of the better results in adaptive control. Really, it's like, go take a course if you're interested, because it's really a good topic. Okay, so Jean-Jacques wrote a great influential book. I thought the chapter introduction was as well as I could possibly have said it. So for constant or slowly varying uncertain parameters, we're gonna estimate the uncertain plant parameters or the control parameters online based on the measured signals. And basically, adaptive control system is a control system with online parameter estimation, right? So what is a parameter versus what is a state variable? You could argue it depends on time constants, but if something's changing slowly relative to the dynamics, then you call it a parameter, and you maybe use different approaches to try to estimate those parameters online and converge to it. And it was interesting to see again in the history lesson in Jean-Jacques' notes. He says in the 50s it was super popular, but then there was that crash of the flight that sort of nipped it in the bud, and then there were some theoretical results that led to his work which was in the last decade in 1991 or whatever. So it's an interesting history, but it really has a lot of similarity. I mean, it is the reinforcement learning problem, if you will, in a lot of cases. They have direct adaptive control, which is policy search, indirect adaptive control, which is fit the parameters of your model and then use it in a controller. All the model-free versus model-based stuff, it's all in the adaptive control literature too. Okay, so let me give you some of the simplest examples. Okay, so there's, I think the most important thing, so adaptive control is doing the estimator I just talked about, the least squares estimator, for instance, but doing it online. So you can write recursive forms of the least squares estimator, which are, so you don't have to just every time you get a new data point, recompute your entire least squares. You have a least squares estimate that can be updated incrementally. They typically look like a small linear filter, but the equations are simple. How do you take that online linear estimate of the parameters and estimate the actual parameters while your controller is doing something, and still prove that the system will do the right thing, despite the fact that you're mucking with the parameters of the plant as you're doing the control, right? And it's a super interesting topic. I would say the one key idea of model reference adaptive control, MRAC, versus the online parameter estimation, which the adaptive control world does too, but is that, in this case, in the MRAC case, the objective is not explicitly to estimate the parameters. So there's one form where you explicitly estimate parameters as well as you can. And then use them in control. The formulation in MRAC, in a lot of adaptive control, is just regulate to track a trajectory perfectly, if you will, and estimate the parameters as necessary. So there's never an explicit goal of estimating the parameters. It's just a goal of tracking a trajectory, okay? And I can give you sort of the simplest example of how those might be different. So you think about a double integrator, which would just be mq double dot equals u, okay? If I want to estimate the mass parameter, the parameter estimation might do something like m hat is u over q double dot. You'd be tempted to do that, okay? Don't do that, right? That's, first of all, you're dividing by q double dot, which you shouldn't do. The q double dot could be close to 0, all these other things, right? So what we're advocating for instead is the least squares solution, right? It's the min over m over some entire trajectory. But I can explicitly write an estimator that tries to minimize m. And like I said, there's online versions of this. And when you're all done, you'll get the mass out, right? If you've written a sufficiently rich trajectory, that is an algorithm that's running with the explicit goal of minimizing some prediction error, okay? The MRAC equivalent, you could write a controller that will track a trajectory of q double dot, a desired trajectory, and it may estimate the mass if it needs to. There are other cases where it doesn't need to estimate the mass and it can still regulate the trajectory. Just depends on what the desired trajectory is. So the MRAC version would try to impose some second order dynamical system. Okay, so let me just give you the basic form of it. I'm trying to see if I can skip some of the jargon. So if I were to write a controller, if I have a reference trajectory, you could write a controller if you had the model that would follow it, which you might write as something like q double dot desired minus some feedback term. So this would make q double dot equal q double dot desired already, but if I have to reject any initial condition error or noise or anything like this, I'll add some PD terms in here. Instead of writing the full PD controller, I'll write a critically damped one. Where q tilde is just q minus q desired. Okay. It turns out if you examine the performance of a controller like this, then you can write a much simpler control law, or update law for M, which has the explicit goal of proving that the trajectory will converge, and it has only a sort of a secondary goal of estimating M. So in practice, the controller will look something like this. You'll write a control law which adapts. The form is going to look a little bizarre, but you don't want to see all of the sliding mode stuff that normally goes along with it. So it's this bizarre, multiply my accelerations times roughly my PD error, okay? But this gives us the guarantee in terms of, so it guarantees tracking. And this is what people do in the full robot case too. But I think it's sort of easy to think about in the very simple case, because in this case, there's a function like a cost to go function. It's a Lyapunov function that people will write, which is actually going downhill the error that you want. It has an incidental term of trying to estimate this is M is the error in your estimate, okay? And you can show that this goes downhill whenever S is non-zero, okay? So the big point there is that you can write controllers which will accomplish the task, but not necessarily have to estimate the parameters. And the example from the book, which I think is quite nice, is even for this double integrator example, if you give it a reference trajectory, which is just trying to drive it to zero, in fact, it can converge quickly enough on that reference trajectory that even though it starts with an unknown mass, this is the parameter M hat estimation, it drives M up in order to try to converge, but at some point it's actually accelerating close, well enough towards the origin that it's absolutely fine tracking with M being the wrong value. It's still tracking the trajectory perfectly, and it will never converge to the real solution. If you give a different trajectory though, that's trying to execute a more interesting trajectory, then it will actually, in order to get the long-term steady state to zero, then it will drive the mass to zero. Now, this is a little bit like the topics that come up in reinforcement learning about how you don't need to learn your model. I mean, when people argue about model-free versus model-based, one of the advantages of model-free is there might be things about your model that you don't need to accomplish the task. I say that when I say I'm buttoning my shirt and I don't want to have to estimate the state of my shirt or the model of my shirt, right? So adaptive control can have that flavor also, right? It can estimate just what it needs to accomplish the task. And in fact, the controller that we saw sort of for Jean-Jacques, throwing the ball, I could assume they didn't publish that version, but the paper catching and the like, they were this the multibody version of that, where it's almost exactly the same. He uses M instead of H instead of M for this. And gravity is G, but it's almost exactly the same. He's got his data matrix times his parameters. He adds a PD term on top of a forward model, and you get these terms, you get a Lyapunov argument of the form like this. So what this means to me when I look at this is that I have a guarantee that the error metric, my error metric, first of all, is a combination of my parameter error and my tracking error, but it only goes downhill when there is tracking error, okay? Because S is my tracking error. It's like the error going into my PD gains. And I'm only gonna try to fight that error. The guarantee I have is that my tracking error will go down, but it never actually tries to estimate the parameters. It will leave residual in the parameters as necessary when tracking the controller. Okay, so there's a lot to know in adaptive control. I think the structure of the equations is so rich that it just doesn't, let's see, I feel torn because I think for really interesting manipulation tasks, it's not clear that you should try to, should start with physics models and fit the parameters. But for something like tossing bananas, I guess I think you should. I think you probably just can pick that up, think of it as a rigid body. All the objects in that are rigid. You can estimate its center of mass. You can design a better trajectory for your robot to execute that and leave with the proper velocity. And I think that the dominant effect of the residual learning, at least in that example, was more about just being, the physics model was too sloppy about where the center of mass was relative to the hand. And and we could have done a better job with that. Any other questions about that?
So just on so this one where you don't have to estimate the parameters is called indirect, right? I just wanted to clarify terminology.
So good. So they're slightly different. So model reference adaptive control is this one. Sort of, I think Jean-Jacques would call it this, the self-tuning controllers would be the other class where you're trying to estimate the parameters explicitly. And then under self-tuning, you would break into either direct adaptive or indirect adaptive, where the direct adaptive would estimate more of the control parameters directly, and indirect goes through the plant parameters explicitly. So normally indirect means estimate the plant parameters and then use it in your controller. That's the shorter answer. And this one is not that. This is design the update for your parameters in order to be able to write a proof that your system's going to converge. And it's not that your trajectory is going to converge, right? So these things are typically motivated by giving some algebra that guarantees that my system's going to converge. And they don't explicitly run through estimating the model parameters.
But I thought direct adaptive control doesn't estimate the model parameters either. So wouldn't this fall under direct?
So yeah, I mean there are ways to write an explicit self-tuning controller parameterized by the control parameters instead of by the plant parameters, which I think I won't. I think it's completely fine to think of that as a direct. I think people would distinguish between this and a direct method. Model reference adaptive is a slightly different thing, but in broad strokes, I would say this is closer to direct than indirect. Yes. What do people think? So does it make you think that you should study the robot? I'm not, the older robot texts, or does it make you think that we have reinforcement learning now, so we don't need this stuff? I honestly wonder. Like, I don't know what the right answer is, but I think this should be in your arsenal if you want. Yes. I think reinforcement learning is incredibly general and powerful, but extremely inefficient. So you should only use it when you don't have more structure. And this is a case where we have lots of structure, basically.
Well, so
Okay.
do you think that, oh, sorry.
Oh, no, you can go, Terry.
Wondering, I'm just trying to understand the logic for why you want to do residual learning, and could it be that, like, when you do sort of online gradient descent to find the parameters, like the physics model acts as a baseline? Is there a connection there?
Oh yeah, totally. Yeah. I think Andy makes that point super well in the paper. It's even in the video, I think it says that the physics model helps to generalize to different Cartesian things very well, and then really just adding something on top of that could capture, for instance, aerodynamic effects and errors in where you've picked up the object. I think the motivation is use as much physics as you can, hope for the generalization of power of physics, and then do a little bit more to capture the slop, right? And I think I think there has been a cultural change where we used to think that the equations of motion gave us almost everything, and you really are capturing slop terms. And I think now we're willing to say that the robot or the equations of motion are doing very little, and we'll throw a lot of it into the residual. But the only reason I think to use the physics-based models is if you can train it faster or it generalizes better. Otherwise, because I think the representational power of a deep network would be sufficient without it.
That's what I was wondering, because I feel like it could your residual terms could arbitrarily dominate your physics terms, unless you regularize it to be small or something.
I think that's super important. Good. So I think the basic insights of this lineage on terms of the identifiable parameters and redundant parameters and the like, I think we're probably getting that wrong in sloppy ways in a more generic learning setting. So I think you're right. So how do you balance? There's often extra terms that people throw in to sort of don't use the network too much or other things, but it gets dicey. Okay, please keep reaching out if you have questions about your projects or anything. We're trying to help. We're very happy to hear from you and help if we can.